Alright, so in this video we're going to go through a column design example for a column that's in a frame. So here we can see the bracing details for the column. If you can see here on the y-axis, let me use the laser pointer here. You can see here on the y-axis it's indicated that this column is braced in the y direction, so we'll assume a braced frame in the y direction, and along the x direction we have a moment frame. Now we're going to be designing this column here on the first floor. For the example, we're going to assume that this column is the same as the one below it, and that's for the purposes of computing our G values for when we calculate K. The beams that frame in on this upper joint are 21 by 83s. They're 45 feet long. We have a pinned boundary condition here on the bottom, and this column is subjected to a dead load of 250 kips and a live load of 735 kips. So to start the problem, the first thing that you'll want to do is factor those loads. So we have a dead load of 250 kips and a live load of 735. So just our familiar load combo, 1.2 times the dead plus 1.6 times the live. Plug that in, so 1.2 times 250 plus 1.6 times 735, and that comes out to be 1,476 kips. Now that's step one. Step two, we need to determine what's going on with our effective lengths. Now, along the x direction, we know that the column length is 14 feet long, but we don't know what K is. And that's what makes this column design example different than the design of a singular column, is that you automatically know what K is. The procedure is exactly the same, but this one fact right here is going to make the problem much longer. The fact that K is unknown, or K must be determined. Now that's along the x-axis. Along the y-axis, the only thing that we know along the y-axis is that we have a braced frame. But that's it. We don't know any of the details regarding the bracing elements. We don't know the stiffness of those elements or the beams. We don't know anything about the y-axis other than that it's a braced frame. Well, from our lecture, you know that for brace frames that K is anywhere between 0.5 and 1. But since we don't know anything other than that, we're going to assume the worst case scenario. We're going to assume that K equals 1. So if K is 1 and the length is also 14 feet, then we have a KL along the weak axis of 14 feet. Remember, in the manual, that's referred to as L sub CY. So forgive me, you'll see me using KLs in the presentation as opposed to the L sub C's in the manual, but it's all the same. Okay, so the third step is to select trial shapes. Now remember, when we select our trial sections, we select them based off of the weak axis or the y-axis, and then we have to go and validate the strong axis. And remember, when we select these shapes, we select sort of a representative family of sections, at least one W14, one W12, trying to evaluate each depth possible. So we'll start off with the W14s. So I'm in table 41A. That's on page, I'm here on page 4-16. And you start flipping through the W14s to find the first shape that works. Remember, to find the first shape that works, what you're doing is you're starting with this value here, this KL of 14 feet. So you can sort of imagining, if you look here at the table, you can sort of imagining highlighting this row where KL is 14 feet. So you're highlighting that row, and you're finding the first shape, the lightest shape that would safely resist that load. So for instance, the W14 by 90 wouldn't work because it can only hold up 1030, whereas the load is 1476. The W14 by 99 wouldn't work. The W14 by 109, the 120 wouldn't work, but the 132 it would, because it has a capacity of 1,510 kips. So we'll say that our first trial section is going to be a W14 by 132. The reason I'm picking it is because it has a capacity of 1,510 kips. Now, as you know, I'm going to have to check this section's x-axis capacity, so I'm going to need a few values in order to evaluate that. I'm going to need its Rx over Ry ratio, which you can get down here at the bottom. You can see the Rx over Ry ratio is 1.67. I'm going to need its moment of inertia about the x-axis, and you'll see why here in a sec. That's 1,530 inches to the fourth, and I'm going to need its Ag, its gross area, which is 38.8. If we were looking at a singular column, we wouldn't need these two values. All we would need is the Rx over Ry. But you'll see here in a sec why we need the moment of inertia and the area for this example. So that's a W14. So we do the same thing for the W12s. So go through that same table again. I'm on page 4-19. Again, highlight that row that's at 14 feet and find the lightest shape that works. And you can see the 106 doesn't work, the 120, the 136. But right here, this W12 by 152, that would be a valid trial section. And I select that because its capacity along the weak axis is 1,640 kips. Now Rx over Ry is a little different. It's 1.77, and we need that moment of inertia and gross area as well. Okay. Now these are two trial sections. Before we evaluate them, one thing I'll mention, that was a W14 section and a W12. Normally you would select a W10 and a W8, but if you look in table 4.1a, these are the pages that show the heaviest W10s and W8s available. You can see the heaviest W10, the W10 by 112, it doesn't work, and neither does the W8, the heaviest W8. So there's no W10s or W8s for this example that were found to be acceptable candidates. So the way so what we have to do from now is we have to evaluate those trial sections. Now, before we get into that, just a note, if these trial sections, if neither of them work, what we would do is go back to that table and select the next heaviest W sections and go from there. But you'll see here in a sec that we won't really have to do that for this example. One of these sections will work, and we'll illustrate that later. Now, we have to evaluate these trial sections. Now, we're evaluating them along the x-axis, and the big difference between a singular column and a column in a frame is that we're going to have to compute K. Now, to compute K, we're going to need to determine G constants for the top and the bottom of the column. So I have the top and the bottom of the column. I labeled them A for the top and B for the bottom. Now, I have no idea what's going on at the top of the column because that's going to change from column to column. But for the bottom of the column, I know that that's a pin support. So the G value, I take that to be 10 because it's a pin connection. If it was fixed, I would take that to be 1. Now remember, what we're going to do is we're going to compute a G value, and then we're going to compute tau, our inelastic stiffness reduction factor. And when we go into our alignment chart, we're not going to go in with G, we're going to go in with tau times G. So for the upper joint on the column, we're going to be computing tau and G and going into the chart with that. However, for the pin support, we just go in with G. You don't apply tau factors to support conditions because there's really no inelasticity associated with a fixed support or a pin support. You just leave it as 1 or 10. But for the top joint for this particular column where there's a beam and column framing into it at that joint, you would need not only the G value but the inelastic stiffness reduction factor. One other point, you don't have to use tau in column design, but I'm going to show you later on why that is really recommended for not just columns in general, but for this particular example. Okay. Oh, one other thing. In order to compute G values for the upper portion of this column, we're going to need information on the beam. This beam is a W21 by 83. Now we know it's 45 feet long, but what we're going to need is the moment of inertia. So, and particularly we're going to need the strong axis moment of inertia. If you look over here on the right, you can see this symbol indicating, this top and bottom rectangle are the flanges sticking out, and that larger portion is the web. So what we're seeing is the column along, or the columns and the beams along their strong axis, so we need the x-axis moment of inertia. So I go into table 1-1. I highlight the properties for a W21 by 83, and what I'm looking for is the moment of inertia along the x-axis right here, which is 1830 inches to the fourth. So before I start evaluating each of these sections, what you'll see is I've just sort of summarized some info over here on the left. So for the girders, for the beams, if you will, beams or girders, I'm using that interchangeably in this example, and you'll see why. The moment of inertia we're going to take to be 1830 inches to the fourth, and that doesn't matter if we're looking at the girder on the left or the one on the right, because they're the same shape. As for the length of the girder, they're both 45 as well, so we can take that to be the same. Now the moment of inertia of the column, that changes depending upon what shape we're looking at, whether or not or what trial section we're looking at. You know, trial section 1 and 2 both have different moments of inertia, but they are both 14 feet long. So when we compute our G values, remember the notation, or the way that we compute G values is we take the sum of the I over L's for all the columns framing into a joint divided by the sum of the I over L's for all the girders framing into the joint. Now to explain what's going on in this formula down here, remember we only need to compute G for this joint here where the laser pointer is at, that upper point, because that's that upper joint on the column. And if you look at that joint, well, how many columns are framing into that joint? Well, there's two, the one from above and the actual column itself. So there's two columns, and how many beams or girders are framing into that joint? Well, there's two. So there's two columns and two girders framing into that joint. But for instance, if you look at the girders, well, they're the same. They're both 21 by 83s, and they're both 45 feet long. And the same thing is true of the columns. We don't know what column we're looking at right now because we're not actually evaluating the sections, but the note that says assume this column is the same as the one below, and they're both the same length, they're both 14 feet long, essentially what we're going to have is 2 I over L's for the girders and 2 I over L's for the columns, and they're the same. So the G value would be computed, as you can see down below, so I over L plus of the column plus an I over L of the column, so 2 I over L's for the columns, and the same thing for the girders. An I over L for the girder on the left, an I over L for the girder on the right, so 2 I over L's for the girders. But you can see I have a 2 and a 2, so I just cancel that. So this slide here, this is just me doing a little bit of algebra to make some of the calculations that I do later a little repetitive and a little somewhat straightforward. So let's just get right into evaluating our trial section. So we're going to start off with our first one, W14 by 132. Now before I get into this, this section is a 14 by 132, and the next section, trial section number 2, is a W12 by 152. So trial section number 2 is heavier. So what that means is that if we evaluate trial section number 1 and it works, we stop the problem, because there's no point in evaluating trial section number 2 if this one works, since trial section number 2 is heavier. So we'll see if trial section number 1 works. If you recall, I just went ahead and copy and pasted the basic info, or the section properties for this column, the Rx over Ry, the Ix, and then the area. So in order to compute K, because that's really what we're after, we have a few calcs we've got to do. The first thing that we've got to do is we've got to compute that G value. So we take the I over L for the column and the I over L for the girder. Now remember, that formula that we're seeing on this slide really only works for this particular example, just because of the way the framing worked. There were 2 beams and 2 columns framing into that joint A that were identical. But if your frame is different, you're going to need to reevaluate that. So I've got all the data here, the I over L for the column and the I over L for the girder. If the units seem a little weird, you're taking inches to the fourth over feet. How can you do that? It's because the top and the bottom of the fraction are the same. You have inches to the fourth over feet divided by inches to the fourth over feet. So as long as your lengths are consistent and your moments of inertia are consistent, you can leave those units in that fashion, and it will be fine. For instance, you might be tempted to convert the lengths into inches so that everything matches, but it's not really necessary because you'd be converting both of them, so it sort of get all divided out. It's really not needed. Okay, So once you plug and chug, you should get a G value of about 2.69. I carried that out a little far. I do that just for the purposes so that when we see the values in the on the slide, that we can sort of remember where they're coming from. So I like to do that by carrying it out a little bit far. Okay. Now the next thing that we have to do is we have to compute this quantity Pu over FYAG. Now the reason that we're doing that is because we need to see whether or not which equation we're going to use for tau. Now when we compute that, first off, this quantity does come out unitless, because if you look on the top, we have kips, and on the bottom we have KSI times inches squared, so that's kips. So this is completely unitless. And when you plug and chug that, you should get 0.761. Now if that value is, now, the equation that you use is dependent upon whether or not that value is greater than or equal to 1/2. And so just to recall, what this fraction tells you is, for this load, about how close are you to yielding the column. So we're about 70%, 76% of the way there towards yielding this column. So this column's got some pretty significant load on it. So because of that, the use of an inelastic stiffness reduction factor is warranted. Now the equation for when it's over 50% is 4 times that fraction times the quantity 1 minus that fraction. And I know you can see this equation and go, well, I have to do a lot of computation here. I have to plug in a lot of values. But think, this Pu over FYAG, you've already computed that up here. It's 0.761. So just take 4 times that fraction times the quantity 1 minus that fraction. So it's 4 times 0.761 times the quantity 1 minus that. So it makes this calculation a lot easier if you just use the value that you've already computed in the previous step. So that comes out to be about 0.73. So take the tau times the G, and you should get about 1.956. So 0.728 times 2.687 comes out to about 1.956. So the next step, once you have this, is to go to your alignment chart. So we go into our alignment chart with a tau value, or a tau G value of 1.956 on one end and a G of 10 on the other. So what you do is you locate that on either axis and you strike a line. Now it doesn't matter whether the top of the chart says GA and GB, but you could flip them and it really wouldn't matter. You could, for instance, you could locate the 10 on the left axis and the 1.956 on the right. It really wouldn't matter. But you locate those points and you strike a line, and then you interpolate and try and see, well, what is the K value given these two entries of G? And so I'm eyeballing this. I'm getting a K value of around 2.1. If your K value is plus or minus a couple hundredths on that, that's really not that big of a deal. Remember, these alignment charts are intended to help you solve those really nasty equations for the alignment charts graphically. So there is going to be a little bit of scatter there, and that's completely fine. So now we finally have our K value. So now once we have our K value, this goes right back to a singular column design problem. So let's recall. You have an Rx over Ry ratio. Remember, we looked up trial section number 1 assuming or based on its weak axis capacity. Now we have to validate its strong axis capacity. So now that we have that K value, we just say KXLX over that ratio of Rx over Ry. So K is now, we're using 2.1, the 14 feet for the length, and then the 1.67 for the ratio. It comes out to about 17.6 feet. So obviously the table doesn't have an entry for 17.6 feet, but it does have an entry for 17 and 18. Now we're looking at the 132. So this is 132, the 17 and the 18. I'm getting a capacity of 1,410 kips and 1,370 kips. And then the next step would normally be to interpolate between those two values in order to determine what is the actual capacity. So if I was eyeballing it, I'd say it's something like I don't know, 13, I don't know, 85, 1386, maybe something like that. I'm just guessing. But here's the thing. If you actually think about it, you don't need to do this interpolation at all. Remember, we're designing this column to withstand a factored load of 1,476 kips. Well, I can look at those two numbers and say I don't care what the exact value is from linear interpolation. It doesn't matter what it is, it's not going to be bigger than 1,476. And we've pulled out all the stops. We used tau B. Remember, we didn't have to use tau B, but using tau B usually means you're going to squeak out a little bit more capacity. You're actually going to get a benefit from using tau. So we've pulled out all the stops. We've used every available resource that we can to see whether or not this W14 by 132 works. And in the end, doesn't matter whether or not it doesn't matter what you interpolate between these two, it's not going to be bigger than that. So we can pretty much say at this point that trial section number 1 is no good. We can't use the W14 by 132 to safely resist that load because it fails along the strong axis. So move on, go on to trial section number 2. And so now that you've gone through this process with trial section number 1, with trial section number 2, the math should go a lot faster because you've already done it once. The only thing I would mention is just really make sure that you're watching the details. It's really easy to pull values from the previous section, and so you really just need to make sure that you're pulling the correct ones. You don't want to pull data from the first section when that section didn't work. Make sure that you're using section properties for trial section number 2 when you're evaluating it. Okay, so first step, same as before, we compute a g-value. The g-value is a little different because the moment of inertia is a little different. It's a 1,430 inches to the fourth section as opposed to, I think it was something like 1,530 last time. So the g-value drops a little bit. The PU over FYAG changes because we have a different gross area. So what that means is that not only is the tau going to change, we're still going to use the same equation for tau because tau, that fraction, that PU over FYAG is still over 50%. But we're going to go through and chug out tau. It comes out a little lower or a little higher, and it's a tau value of about 0.9, actually comes out to 0.897, and then tau G comes out to be, we take that 0.897 and the 2.512 and chug that out, we get about 2.25 for tau GA. So we have tau GA, again the GB on the bottom of the column, that doesn't change, it's still a pin support, so GB at the bottom is still 10. So we take those two values, strike a line, and then we interpolate to see what our K value is. K looks like it's a little bit larger than what we got last time. I think I called this at about 2.15. That's just me eyeballing it. Again, plus or minus a couple hundredths is fine, but that based on what I found, that's about what I'm calling it there. Next, now that we have our K value, again it goes back to the same as a singular column. We compute our KXLX over RXRY. So we take our new K value of 2.15 and we have a different RX over RY ratio of 1.77. So K equivalent comes out a little different. It comes out 17.01 feet. So that's really close to 17. But let me pull the value. So again, this is close to 17. It's not quite there. So if we looked up between 17 and 18, we'd get 1490 and 1440. Now, to be honest, technically, I guess I would say that you would need to interpolate that, but I can eyeball that and see that between those two, 1490 and 1440, we're probably going to get a capacity something like 1489, 1488. Again, really, really close to the 1490. And recall our load. Our load is 1,476 kips. So comparing those two, I think it's a pretty safe assumption that even if the capacity was 1480, and it is certainly not that. Looking at that interpolation, it's probably closer to 89 or 88. But looking at that, I think it's safe to say that trial section number 2 is good. And so trial section number 2 is going to be our section. Now we have done a lot of math, we've done a lot of computations, and so I would strongly advise that if you were actually going to use this column, that you take the time to evaluate the capacity of this column according to the equations in Chapter E. Just because you want to use another method to ensure that you're getting around the same capacity. I mean, the capacity should be about 1489, 1488, something like that. So equations in section E3 should generate that. And it's a completely independent means, or a somewhat independent means of verifying your calcs. I would definitely do that. I do have a couple of notes that I want to just sort of close the example out with and just sort of make some points to make sure that everybody understands sort of the broad scope of what we discussed. First off, I want it to be clear that we assumed the worst case for the y-axis. Remember, the y-axis was a braced frame, and we've just, up until now, just been assuming that ky is 1. That's actually the worst case scenario. Remember, ky could be anywhere between 0.5 and 1 for a braced frame, and we assumed the worst case is 1. But here's the thing. It really didn't matter in the end what was going on with the y-axis. Again, we assumed the worst case scenario, and if you compare KY-LY with KL equivalent, you found that KL equivalent was always larger. Remember, the reason that we compute a KL equivalent, this KXLX over RX over Y, is so that we can compare apples to apples. So essentially, when you look at KY-LY and this KL equivalent, they're basically an apples to apples comparison to illustrate which axis governs. So what we found with both of these trial sections is that the strong axis governed the capacity, and you will determine that if you go through the brute force method of using section E3 and the equations in the spec. You will find that the KL over R for the x-axis is going to be bigger than the KL over R for the y-axis, and the reason why is because just look at this. So I guess the point I want to make here is that the assumption that K is 1 along the y-axis was a completely valid assumption for this example, not just because it makes behavioral sense, but because it didn't matter what was going on with the y-axis. The x-axis governed, as you can see here. Finally, one other point I'll mention. We used tau in this example, and we just sort of blanketly assumed that, or we just blanketly used tau for every trial section. A longer way of doing this example, it would make the video a lot longer, would be to take each section and see, well, what happens when you don't use tau and what happens when you use tau. Well, the short answer is every single time that you use tau, you will squeak out more capacity if the strong axis governs, pretty much every time. Especially in a scenario like this where you're assuming K is 1 along the weak axis, so tau doesn't come into play along the weak axis, so really tau is only going to affect your strong axis capacity. And if the strong axis governs, if you have a KL equivalent larger than KY, you will squeak out more capacity with tau. And for this particular example, what you'll find is that if you actually go through trial section number 2 and you don't use tau, you'll find that trial section number 2 does not work. So, using tau can actually be the difference, actually mean the difference between selecting one shape or not. And it's not only is it completely allowed within the specifications, but it makes behavioral sense to use tau. I mean, columns exhibit inelastic behavior, so capturing that in your analysis is a completely valid and reasonable thing to do. So short answer, or the final answer for this example, is to use the W12 by 152. Again, I highly stress that you validate that math using section E3 of the spec. But yeah, if you have any questions, we'll discuss that when you get back from spring break. That's all I have.